Welcome to Calculus. Today we will investigate determining where on its interval of its domain does a function increase or decrease. We'll take a look at two examples, and we'll start with a cubic function, f of x equals negative x cubed plus 3x squared plus 4. So we are interested in saying, okay, on the graph of a given function, how do I know where the y values are increasing as I move from left to right over my domain? Where on that interval is my y values of the function decreasing? That's kind of what we're after. So we do need to graph the function. Let's begin by completing that task. Let's create a table of coordinate points to create the graph of f of x. So x, f of x, and we'll just place from -2 to +2 since we don't have a given interval to calculate there. And we'll just plug in our x values into the function. So -2 cubed, so that's going to be -8, plus 3 times -2 squared. So that's going to be a value of 12. So that's got a value of 4, plus 4 is going to be 8. Let's plug in -1, so -1 cubed. So that's going to have the sign here. I think I miscalculated on that first one because this -2 cubes -8 times negative is +8, plus 12 is 20, plus 4. So that'll be actually 24. Let me correct that real quickly. All right, so we're squared away now. -1 cubed, that has a value of +1, plus 3 times -1 squared. So that's 4 plus 4. This has the value of 8. Now we'll plug in 0. 0 is easy to calculate with because it's going to cancel these first two terms. So that output's just going to be 4. Then we'll plug in 1. -1 cubed is -1, plus 3 times -1 squared. So -1 plus 3 is 2, plus the 4 is going to give us 6. And then lastly, plugging in +2, so that first term will be -8, plus 3 times 2 squared. This is going to be 12. Total of 4 plus 4 there is going to be 8. So let's go ahead and graph. We can't do a whole lot with -2, 24, but we can start graphing with -1, 8, 0, 4, 1, 6, 2, 8. And let's go ahead and calculate for 3 as well. So -3 cubed. So that's going to be -27, plus 3 times 3 squared. That's going to be 27. So those two cancel out, plus 4 equals 4. So we are looking for that decrease down to 4 at 3. And so our function, if we were to just sketch the graph, would look something like this. And that's a very typical cubic function where it's got the double wave in the center of the graph. So we can see just roughly where the function's increasing, decreasing. It looks like the decreasing is from -infinity up to somewhere around 0. And then it picks up again somewhere around +2 and decreases forever towards +infinity in the x. And then it appears that our increasing interval is here in the center from about 0 to 2. So our task is to figure out what exactly are those intervals. Well, to do so, we just need to think about how the derivative gives us information about a graph. So let's just state for ourselves how we know whether a function is increasing or decreasing. And it's really by this rule of thumb. So increase, decrease. If the derivative of a function has a value that is greater than 0, then the function is increasing. If the value of the derivative is less than 0, the function is decreasing. And just really by those two simple rules of thumb, we can make really solid algebraic claim about whether a function's y values are going up or going down as we read from left to right across the domain. Well, in any case, what we need to do is take the derivative of the function. So let's do that right now. So the derivative of f of x, since this is a polynomial function, is going to be negative 3x squared plus 6x. And so what we really need to determine is, where is this function going to be positive? Where is it going to be negative? So that's a quadratic. And really what we need to do is find its zeros. So what I'm going to do is I'm going to set this equation equal to 0. So in fact, I think let's just go ahead and set up a table for this function, for the derivative of the function, and graph it. And that should reveal for us the zeros. I think it's around x value of 0, and then at 2 where we see a change in the increase decrease of the original function. So let's just go from negative 2 through 2 like our table for our original function. So again, I just want to calculate. It's going to be negative 3 times negative 2 squared. So that has the value of negative 12, plus 6 times negative 2. And that's going to be negative 12 as well. So it has the value of negative 24. Not really graphable, but we got it in our table. Negative 3, we'll plug in negative 1. So that's a value of negative 3 plus 6 times negative 1. That's negative 3 plus negative 6, that's negative 9. And then at 0, both of those terms are going to cancel out because they both multiply by 0. So that actually is going to hit the x-axis right at the origin. And then at 1, the function is going to become positive. So that negative 3 plus 6 is 3. And at 2, let's see what the output is there. So I'm going to plug in 2 squared. So that's negative 12 plus 6 times 2 is positive 12. That's back to 0. Let's also calculate it 3. So negative 3 times 3 squared plus 6 times 3. So that's going to be negative 27 plus 18 is negative 9. So we can see that quadratic symmetry. And we'll go ahead and plot that function just so we can see how it looks. So at negative 1, it's negative 9. That's a little off my graph, but I can approximate it. 0, 0, 1, 3, 2, 0, and then again 3, negative 9. So this is the graph of the derivative, and what we need to do is just interpret it based on our two rules of thumb that we wrote here at the outset. So I'm going to find the places on the derivatives graph where it's less than 0, and I'm going to highlight that in green. That should correspond with the places on the original function where it's decreasing. So I've got that left arm from negative infinity to 0, and then this right arm from 2 to positive infinity. And that really confirms what we had given as a hypothesis. So let's go ahead and finalize for the decreasing. So f of x decreases on the interval from negative infinity to 0, or from 2 to infinity. And then similarly, we can find the place where the derivative has a function or y value greater than 0, so above the x-axis, and that's that interval from 0 to 2. And again, it matches what we saw with our graph. So we'll just finalize our increase statement. F of x increases on the interval from 0 to 2. I'll box that. That ultimately is our answer. So that's a nice cubic function. Let's take a look at another cubic function that's presented within an absolute value. So here we've got f of x equals absolute value of x cubed plus 3. So what we should do first of all is just graph this. So again, let's just create our table just to see what does the original function look like. So we'll put x and f of x. And again, we'll just set -2 through +2 since we don't know much about the function. And we'll just plug these in. So I do have the absolute value bars, -2 cubed plus 3. So -2 cubed, that's -8, plus 3 is -5, which within absolute value is going to exit as positive. So -2 is at +5. -1 cubed plus 3. So that's going to have a total value of 2, which is just going to be 2. Then with 0, so 0 cubed plus 3 is going to equal 3. And then we kind of get a sense here, these are all positive values, so I don't really have to do much with absolute value now. That's just 4, and then 2 itself, if I square, or cube 2 rather, is 8 plus 3, that's 11. So I really kind of need to think about how this is going to look on the graph. Basically, it's this cubic function x cubed plus 3 with everything that would have been below the x-axis reflected up. So I am interested in kind of the 0. Now, I haven't caught the 0 of the function here in my table, so I am going to go over to Desmos just to see, because that is an irrational number where this graph is intersecting the x-axis. So let's catch that x-intercept to add to our list. So I'm going to put in the function. It's f of x equals the absolute value of x cubed plus 3. So I can kind of see the shape here of the absolute value, or the cubic function rather. And we got our list of values there. What we need to say is between -2 and -1, what is this place where the graph is crossing the x-axis? So that's the cube root of -3. If we were to solve that out, it's very irrational, -1.442. I just want to catch that one value. So let's take that information back to our graph and finalize the notes there. So I do want to include that point we just found. So it would go in between -2, -1. It's -1.440. So that's a good point for us to catch. Since this function, it behaves uniquely because of the absolute value feature. So there's -2.5. We're going to plot this, -1.44. That's where the original function would have crossed the x-axis, but notice it's reflected that left side up. And then it continues to reflect, or at this point, this is the original absolute value graph. So not at 3, it's at 2. And then at 0, the graph's at 3, 4, and then 11's off my screen. So if I were to graph this function, there's the reflected piece, and then here is the cubic function. So that's our original function there. It's unique because of the feature of the absolute value. It's specifically reflecting this left-hand piece, which would have been facing downward, it would have been decreasing. So again, what we need to do is just say, where do we think this function is going to be decreasing? Where do we think it's going to be increasing? So I'm going to grab the highlighter here. So I believe that it's decreasing along this interval here. The piece of the graph that's been reflected up, and then the increase looks to be everything to the right. There's no other part of the graph where it's decreasing. So our hypothesis is that we've got two different intervals here, but let's follow up with the algebra. Let's find the derivative of the function. So first of all, we'll find derivative of f of x. So to take derivative of absolute value, I got to keep in mind that that is equivalent. Let me write something over here. So if y equals absolute value of x, I could write that as the square root of x squared. Those are equivalent mathematical operations. So that's what I want to do here. I want to convert this over to the square root of x cubed plus 3 squared. And let me say that's not the derivative, that's the original function. So now let's take the derivative of this version. So this is going to be f prime of x equals, so I'm going to take the derivative of the square root. So that's going to be half as a coefficient times the base, which I won't change right now, x cubed plus 3 squared to the power of negative half. But then I do need to apply chain rule to take derivative of the interior. So that's going to be times 2 from the old power, x cubed plus 3. Then again, I need to apply chain rule a second time to take derivative of the very innermost composed function. So that's 3x squared. So now we want to simplify this. So I do want to notice that the half multiplied with the 2 will cancel. So in the numerator, we've just got this in the light blue. So I'm going to put the 3x squared first times x cubed plus 3. But then this x cubed plus 3 squared to the power of negative half is going to descend. And as it goes to the denominator, that power of negative half is going to become positive. But then here at the end, I need to then convert this back over so that it is equivalent to the absolute value. So the numerator is not changing, 3x squared times x cubed plus 3, but now over the absolute value of x cubed plus 3. So that's our derivative. Let's go write that down and let's get a table from Desmos. There's quite a bit going on there. And let's spend our time doing the analysis instead of graphing. So I want to get a graph of this derivative. So we'll call it g of x for Desmos. 3x squared in the numerator times x cubed plus 3. Make sure that that's not all in the power. And that's all over the absolute value of x cubed plus 3. So here's our graph. We really need to notice what's happening down below. So notice the parabola, it is a quadratic, but because of the absolute value in the denominator, I have a reflected piece. Really, it's right where that original function hits the x-axis. Let's get a table for that green derivative. And I also want to include the point that we found, which was the cube root of -3, which should be between -2 and -1. So we'll do the cube root of -3. And we can see that that's included on that upper part. And notice that it's really not included down here. So my upper version's positive 6.24, my lower version's negative 6.24. It's really a reflected version. So I'm going to write that table down. So -2's at -12. The cube root, of -3 has the output of 6.24. On the upper side, on the lower side, it's -6.24. And then the rest is the quadratic unaltered. So -1, 3, 0, 0, 1, 3, and 2, 12. So I've got the table for this derivative, and I'm going to head back to the notes just to finalize what we've got going on here. So again, what I want to record is this table that we just found on Desmos for the derivative. So it was -2, -12, and then we had the cube root of -3. And that is equivalent to this -1.44 that we'd found. So we'll say that had the value of -6.24 below, 6.24 above. That's where the reflection is occurring. And then -1, 3, 0, 0, 1, 3, and 2, 12. So we'll just graph that, and then we'll write our statements of increase and decrease. -212 is pretty much off my screen. I can estimate that it's about there. At about -1.44, I have the value of -6.24. So this lower half terminates right there, and then the function picks up at positive 6.24. And then at -1, it's at 3, 0, 0, 1, 3, and then 2, 12. So this parabola on the right-hand side is as normal. And that confirms what we were saying. So on the derivatives graph, the part that's decreasing is this part that is negative. And then the part that is corresponding to the increasing portion of the original graph is the part of the derivative that's positive. And so for this one, our function decreases on the interval from -infinity up to the cube root of -3. And then f of x increases on the interval from cube root of -3 to positive infinity. And that concludes our description of the increase decrease of this original function, the absolute value of x cubed plus 3. Thanks for joining for this investigation of where functions increase and decrease on their domain values. See you soon.